I'm Enoch Kotedomo from the University of Jinan, and I will be presenting shortly our paper, MedDef, an efficient self-attention model for adversarial resilience in medical imaging with unstructured pruning. And these are our co-authors and author. So we'll just run it through quickly. And this is our content, introduction, MedDef framework, adversarial training setup, data set evaluation, experimental results, and conclusion. So, what is our problem? Like, we know that medical imaging in AI system achieve exceptional diagnostic accuracy, but remain vulnerable to adversarial attacks. And it is for such reason we are proposing a MedDev to help um, cover some of these challenges that we are experiencing. The It is very hard for medical images to distinguish adversarial noise from critical medical features. Like we can see in here, when a particular medical image, let's say, is experiencing an attack. Like for an example, you have a normal image and then a perturbation is applied to it. It will be difficult for medical devices to determine if that particular image is actually safe. So you can see a normal image from here, and after applying a noise to it, you have a pneumothorax. So that is a challenge. And we introduce MedDef, which is a defense-aware attention mechanism that integrates adversarial robustness directly into feature processing. And this complete DAAM, as we call it, comprise of three cooperative components, and they include adversarial feature detection (AFD), medical feature extraction (MFE), and multi-scale feature analysis. And these are their major contributions, like the works that they are doing within our proposed mentor. AFD suppresses adversarial noise while preserving diagnostic features through selective attention marks, and as well, MFE enhances edge and textual cues using medical domain knowledge, and lastly, multi-skill uh, feature analysis coordinates defense across multiple spatial resolutions. So moving on, this is more like the flow. We have uh, like a 3D stage architecture format. Firstly, with our processing, and then we have the second stage to be our model stage, and after that we apply our unstructured pruning in the third stage. So this is basically the first stage where we have image being processed, and we have adversary images being generated. Here you have your generator and your discriminator, and this is just the adversary generation process. And after that, you have both the clean image and the fake image being inputted into our model. And once it is into our model, we have the initial part of it, because we use ResNet backbone as our backbone model. We use ResNet as our backbone model, and particularly 18. So you can see from this particular architecture, you have the ResNet backbone as A, and after that, uh, you have the defense model, and this defense model is just the DAM integration we added, which is our adversarial feature detection, our medical feature extraction, and multi-scale feature analysis. So this is the next stage, and after that, they are being fused together, and you can see that is for the C. And after this stage, you have uh, them being uh, combined with in the residue, and after that the self-attention is being applied to it, the global pooling, uh, and they are being concurred together, and after that the classifier. And These are the various areas of each of them. You can see that the adversarial feature detection is applying a noise max or maybe a detector directly within the model. Yeah, and also this MFE is also applying edge detector and textual analysis to help make the model very smart whenever it experiences an attack so that it can give some accurate detection. And overall, this is like the flow of our model. And this is our adversary training setup. We did our setup where we applied 35% training data. We expose it to attack, and then 70% of our validation set was also exposed to attack, and then 100% of the test set was exposed to attack. And we use PGD for our entire adversary training process. So we only use one attack, and then we evaluated on multiple attacks. So we evaluated on all of these, like FGSM, PGD, BIM, and GSMA. And our first data set, our OCT data set has about 84,484 images with 4 classes, while the chest X-ray has 5,856 images. So we did our evaluation on both of these data sets. And after our experiment, uh, MedDef achieved exceptional robustness, like 99.97 accuracy against PGD, yeah, which is a very strong attack, and then 98.83% on chest X-ray, while maintaining high diagnostic accuracy. So, as you can see from this is more like the attack success rate versus pruning that we did. So, from 0.0 prune up to 0.8, and then the success of it, we can see that it is BIM that went up to 70 plus from this prone 0.6 prone, and the rest of the others, they were all below 60. Yeah, below 60. All of the other attacks, GSMA, PGD, GSM. And for the checks X-ray, like, they did not reach the point of 50. Yeah, so the attack success did not cross 50, but they were less than 50, as you can see from this visualization. And this was more like our metrics, our per class metrics. And this is for the first data set and the second data set. You can see their performance are all in the 90s and 100%. Yeah, both precision, recall, and everyone's score, showing how good our model is. And then we did an attack intensity analysis where we use 0.01 epsilon and 0.05, 0.1 as a means to really check whether our model is doing well on a stronger attacks. And as you can see from the various results, our full MedDef, which is our complete result from the DAAM, yeah, incorporating all of them, you can see they perform well over the rest of the others. Some other areas, they did not do so well, yeah, but at most places, they did well. Our model did well. So this is just more like an ablation, a study of the different models that we have. And the same for the checks X-ray data set, as you can see the various results. So moving on to the attack success rate. So we did analysis on 30 prone, 70, and 80 prone, and see how well the models will perform. And this is the result of the ablation studies we did. And as you can see, our full DAM, which is the MedDef, uh, it is performing very well over the rest of the others. So with that in mind, we will conclude by saying MedDef demonstrates that adversarial robustness and diagnostic performance can be achieved simultaneously through integrated architectural design. And the complete implementation of our workflow is available on GitHub at this particular URL. So if you check it out, you will see our complete work. Thank you.